Okay, here are some more applications of functions, but these applications aren't necessarily for quadratic function. The first one is, but the second two are not. So let me go ahead and share with you these examples. Number one says a farmer has to construct a branding corral for his cattle, and he plans to use the riverbank for one side of the corral. He has 500 feet of fence to use for the other three sides. Write a function that represents the area of the corral in terms of one of its sides, and then find out what dimensions the farmer should use to maximize the enclosed area. Okay, so really we've only going to have three sides. So I'm going to let this side of the corral be X, so therefore this side would be X as well. And the riverbank, there will not be any fencing used on the riverbank, so that's just going to be a drop-off or a beach for the cows to go get a drink of water. And then here we're going to have another piece of fence to close off the front side of the fence. So actually you can see here that if I use all of the 500 feet, then that would simply be X plus L. So we know that 2X plus L equals 500. And we can easily solve for L in terms of X. Just subtract 2X from both sides, and we get L equals minus 2X plus 500. Now, our objective is to maximize this area, and this area would simply be L times X. So the area here, you see I wrote the area formula L times X. But since we know L is minus 2X plus 500 from up here, then we can replace L and get minus 2X plus 500 times X, and then you can distribute the X through and get minus 2X squared plus 500X. Okay, so now we're going to move over here and we're going to actually find the value for X that maximizes this function. You can see it's a quadratic function and it opens down, so therefore it's going to have a maximum. So to find the maximum, we just use our vertex formula. X equals minus b over 2a, so we have minus 500 over 2 times negative 2, and that's going to give us 125. And then if you can actually plug 125 back into your formula for L to get the length. So negative 2 times 125, that would be negative 250 plus 500. So we would end up with 250 for L. And so the dimensions are actually 125 feet by 250 feet. Now if you wanted the area, the maximum area, you could actually get it two ways. The easiest way, since we know what L and W are, is just to multiply those together to get the area. But if you wanted to do it a more difficult way, you could just take the 125 and plug it into this area function here and evaluate this function at 125, and it would also give you the area. But either way, you should get the same value, 31,250 square feet. Okay, so on the next one, we have a steel drum in the shape of a right circular cylinder, so it looks like this. And it's going to have a volume of 100 cubic feet. So what we want to do is express the amount A, the area of material required to make the drum, as a function of the radius R of the cylinder. So I don't actually have the radius written down here, but basically the radius would be the distance from here to the edge of the cylinder. And so that would actually be your radius right there. Okay, now how much, and there's another question too. It says how much material is required if the radius is 3 feet. So we'll figure that out once we get the function. Okay, so if the area of this cylinder would be the area of this side portion here, which would be, this portion right in here, and then plus the area of the top circle, and then plus the area of the material on the bottom circle. So let's talk about those circles first. That's easy to do. You know the area of a circle is pi r squared. So the area of the top circle is pi r squared. The area of the bottom circle is pi r squared. So if you add those together, you get 2 pi r squared. So the only really complicated thing about this is thinking about how do you find the area of the side portion. So to find the area of the side portion, pretend like we took a pair of scissors or metal cutting scissors, and we cut down through here just a straight line. And let's assume we took the top and the bottom of the can off, and then we draw this, we do this cut right here, and then we're going to unfold this side portion. And when we unfold this side portion, it's actually just going to be a rectangle. And the one dimension of the rectangle is just the height of the can. So you can see I listed h here. That's the dimension from here to here. Now, but what's interesting is when you unroll this, the other dimension is simply the area around this circle. So the area around the circle is called the circumference. So that circumference would be 2 pi r. So the dimension from here to here would just be 2 pi r. So now we know that the area here would simply be 2 pi r times h. So now we've got the area of the side portion, and so the area of the side portion is 2 pi r h, and then add that to the area of the top and the bottom, which we said was 2 pi r squared, and that's our formula for area. But the problem is we've actually got two variables here. Remember, pi is a constant, but r and h are both variables. So I need a way to replace one of these variables, and that's where the fact that we know the volume has to be 100 cubic feet comes in. So what I can do here now is I can go to the volume of a cylinder formula, which is pi r squared h, and we know that volume has to equal 100, and then all we have to do to solve for h is simply divide both sides by this portion, pi r squared h, and then that will isolate the h. So we'll get h equals 100 over pi r squared. Now that we have h, we can just go back to our formula here for area and replace h. So we go back to this formula, replace h with the 100 over pi r squared, and then we can do a little bit of algebra here. We know the pi's will cancel. We know if we divide r from the numerator into r squared for the denominator, we'll just get r. And so we'll get 2 times 100, which is 200 over r for that term, and then 2 pi r squared would be the rest of the function. So now we have the function here written solely in terms of r, and so the area is 200 divided by r plus 2 pi times r squared. So once we have this function, answering the second question is just a simple matter of plugging 3 in for r. So if we plug 3 in for r, we get 200 over 3 plus 2 pi times r squared, and so that would be 3 squared is 9. And so just grab your calculator and see what 200 over 3 plus 18 pi would equal, and it turns out that it's going to be about a little over 123 square feet. And it's square feet because we're dealing with area when we're talking about the area of the material. Okay, the last example here says a box is made up of a 20 by 20 piece of cardboard. So we know that here the dimension from here from one end to the other is 20, and also the dimension here from top to bottom here is 20. And so what we're going to do is we're going to cut squares out of each corner, and so I've highlighted the squares in red. So we're going to cut a square out of each corner, and the size of the square we're going to cut is going to be x by x. So that's the dimension of the squares. And so we want to express the volume of the box as a function of these x by x cutouts. So now what I need to do is let's think about what the base of the box will look like if I cut these squares out and then fold the sides up. So if I cut the squares out and fold the sides up, the base of the square would look something like this. And then that would make the dimension of each side of the square. So let's say the dimension here. Well, we know the distance from here to here is 20. So let's start with 20, but then we know we're going to subtract off x here and subtract off x here, so the dimension would actually be 20 minus 2x. And so the dimension of each side of this square would simply be 20 minus 2x. And also, when I fold up these sides, the height is going to be x, because this dimension here is x. So when I fold up the sides, the height is going to be x. So therefore, the volume of the box would just be the product of the sides, 20 minus 2x times 20 minus 2x, times the height of the box, which is x. And then if you square this or multiply 20 minus 2x by itself, you get 400 minus 80x plus 4x squared. And then if you multiply that by x, you get 4x cubed minus 80x squared plus 400x. So now we have the volume of the box written in terms of the dimension of the x by x cutouts. Now, we're not going to do any more with this, but something that might be interesting to know is that you could actually take calculus. If you had calculus knowledge, you could actually find the value of x here that would actually maximize this volume function. Now, we can't do that in here because the only functions we know how to maximize are quadratic functions, and since this exponent is 3 instead of 2, then we don't have the tools to maximize it. But again, if you were in a calculus class, you would have the tools to maximize this function. Okay, so that completes this video on these 3 function applications.